Comes on, everyone. Let's start off. Let's start off with the problem. An ideal gas undergoes an adiabatic process where Cv is A plus Bt. So Cv is not constant. This Cv is changing with temperature. A and B are constants. T is temperature in Kelvin. Find relation between temperature and volume. Let's get this. Tonight, 11 o'clock is the deadline for the exam. Make sure to give it. Lakshika, do adjust your camera a bit. I can't see you. Make sure your faces are completely visible, everyone. Vartika, same thing. Please adjust a bit. Lakshika, you also still need to adjust. Palaksh, Malika. Your face includes head, eyes, chin. All should be there. That is how we caught last time someone was eating secretly. See, Utsa is eating secretly. Yeah, that is fine. Chalo. How do you do this? This is not any regular process that we know of. C is depending on temperature, and it is an adiabatic process. How do we proceed? You said it's an adiabatic process, so start from there. dq is du plus dw. So cv is a plus bt. So dq is du plus dw, dq is 0. This is ncv dt plus pdv. cv will be n into a plus bt dt is equal to minus pdv. But we already know it's an ideal gas, so pv is equal to nRT. Now see, the main idea is in the question it is mentioned, find the relation between temperature and volume. Means you don't want pressure. On the left hand side, there is no pressure ka term. Right hand side also, let's eliminate the pressure ka term. And then cancels. T comes this side. A by T dt plus B dt minus R dV by V. Integrate on both sides. That would be A ln T plus Bt minus R ln V plus some constant. On T power A. Bt plus R ln V. T power constant is a constant only. So temperature to the power of A, volume to the power of R, and E to the power of Bt is constant. That's the relation. Check. Options will be like this only. Clear? Next one. Why will you consider pressure as constant? Is it an isobaric process? Then
So then won't work be P2 V2 minus P1 V1?
where do you get that from?
So for adiabatic process, the work is P2 V2 minus P1 P1 by 1 minus gamma.
Okay, but this is dW. This is not work done. This is not delta W. This is dW. What you're saying is integral PdV, right? Same thing, but we don't use that here. You don't even know what gas it is, isn't? Nothing is mentioned. So clear? Next one. Question is anyway, find the temperature in terms of volume, na? So pressure ka, don't bring anything in terms of pressure. And second thing here, gamma is also variable. For example, see, Anika, CV is what FR by 2. And you're saying here it is A plus BT. Means your degrees of freedom itself is depending on temperature. Your gamma is 1 plus 2 by F. So gamma is also changing with temperature. So it doesn't work. So that formula was derived under the assumption gamma was constant. That way. So this is a kind of little different thing. So we have a piston here. Movable, massless, insulated piston. The whole vessel is insulated. Initially, this side is P naught, P naught, T naught, helium, and helium. You have a heater. So when heater is switched on for some time, so heater is switched on for some time and then switched off. The pressure in the right compartment becomes 243 by 32 P naught. Find the final temperature of the gases. And find heat supplied. Let's get this. Hope the question was clear. Initially, both the gases are identical. P naught, V naught, T naught, and this thing. So when the heater is switched on, the pressure on the right side becomes 243 by 32 P naught, meaning it's actually getting compressed. Try. I'll give you 2 minutes. Any answers? This was something like this was asked in JEE. Always, what do I say? Always draw the final diagram. So let's start with that. So when I draw the final diagram, in physics, that's the most important thing. If you don't know how your final diagram looks like, there is nothing you can do then. Let this volume be, now see, you're saying this pressure is 243 P naught by 32. Let the volume be V2, temperature be T2. Agreed? Now, if the pressure is 243 P naught by 32, the pressure here also is same, 243 by 32. Because the piston is massless. Let the temperature be T1, volume is V1. So this is P2, this is P1. P1 is equal to P2. Since piston is massless, it is in equilibrium. Next thing, volume V1 plus V2 should be 2V0. Total volume is still conserved. Now, if you take gamma of the helium gas, 1 plus 2 by F, F is 3 because it's helium. That is 5 by 3. Now, if you look at this, can you tell me what process is the right compartment undergoing? The right compartment is undergoing adiabatic process now. Because there is no heat being transferred through the walls. This is insulated. The walls are insulated. The only way it is getting energy is the piston is doing some work. Right compartment, right? The gas undergoes adiabatic process because there's no heat transfer. The left side gas is getting heat, okay? Right side gas is not getting any heat. So we can apply the formula P1 minus gamma, T per gamma, P initial, V initial is equal to constant. So I can write this thing as P naught, T naught, gamma by 1 minus gamma is equal to, finally it is, or let me write it the other way around. P 1 minus gamma T naught is equal to P final is 243 by 32 P naught 1 minus gamma by gamma T2. 1 minus gamma by gamma is 1 minus 5 by 3 by 5 by 3 minus 2 by 5. 243 is how much? 3 power 5, no? 3 by 2 whole power 5 into 1 minus gamma, that is minus 2 by 5. P, this will cancel. 5 will cancel. You end up by 3 by 2 whole power minus 2. So minus 4, when it goes up, it will become 9 by 40 naught. Check. That's the reason the numbers are so weird. 243 by 32, it is given so that it will cancel off. Now what? Now you have to find the heat produced, heat supplied. This is the temperature in the right compartment. What about the left compartment? Question still not over. Try. There, I showed you one how to do. Now you find the temperature on the left compartment and you find the heat given by the heater. Anyone not clear with the steps, please ask me. All that I did is simple adiabatic process. We did nothing there. Generally, whenever they ask you, the heat supplied by the heater, you have to find the temperatures of all the gases. Give it a try. We'll do one more like this. Find the temperature of the left gas and the heat supplied by the heater. Anyone not convinced with this? Aryan, Anika, clear with this? Got it, na? Maulika, Rehan, Vidyut, Yasha, clear, na? Chalo, try. Any answers? How do we proceed? What we have to find in the second part? You're not reading the question, God. Find the temperature of the gases. We found the temperature on the right side. You have to find the temperature of the left compartment and the heat supplied by the heater. Clear? You got disconnected, yeah? How to find the temperature on the left compartment? Any ideas? Now, for the same thing, right compartment. I can also write PV per gamma is constant. So I can write here P naught, V naught, gamma is 5 by 3 is equal to 243 by 32 V naught, V2 power 5 by 3. So V2 will be 32 by 243, 3 by 5 V naught. That is 2 by 5, 2 by 3, 2 by 3 whole power 5 into 3 by 5 V naught. That is 8 by 27 V naught. And we know V1 plus V2 is equal to 2 V naught. From there we'll get the what is this thing? 46. This is the volume in the left compartment. Now go to the left compartment because see, the left compartment, right? We don't know what process is this. So we are going to use P1 V1 by PV by T is equal to constant. Basically, we are equating the number of moles. So initial pressure is P naught, volume is V naught, temperature is T naught. Finally, pressure is 243 P naught by 32, and the volume is 46 by 27 V naught, and this will be your temperature T1. From here, I get T1 there. Oh, you got 207 by 16. That's so weird. Okay, but there you got T1 from here. Clear? If you see it is all just formulas, you just need to apply the formulas in a certain sequence and you start getting answers. What about the heat supplied? Now see, whatever heat you supply, the entire heat is taken by the left gas. And left compartment did two things. One, it is used to change its internal energy delta U1. Then it gave the energy to the piston. And what did the piston do? Piston started compressing the right side gas, and it used to change the temperature of the second gas. Indirectly, the total heat produced will be the total change in internal energy of the gas 1 and gas 2, which is simply NCV T1 minus T0 plus NCV T2 minus T0. Isn't it? Think about it. Where will the energy go? Whatever heat I supplied, that is used to change the temperature of both the gases. So the total heat supplied will be change in internal energy of both the gases. I know T1, T2, substitute and you're done. CV is FR by 2, so that also you know. Have a look at this. Let me give you one more like this. Clear? Everyone got this? What we did? This is again, remember in last class we did cyclic process efficiency. Those are one models. This is another type of models. So these are two different things which are very important in thermodynamics. Remaining things, right, are like this is another type of questions. They mostly talk about molar heat capacities. But especially if you ask me, these kind of questions where you have pistons and all, I'll give you even a better version of this. We will not solve it fully. We'll just write the equations. So let's say we have two pistons. This is connected by a spring. P naught, V naught, T naught, P naught, V naught, T naught, P naught, V naught, T naught. The spring is in natural length. We'll call it compartment 1, 2, 3. The whole system is insulated. Spring is in natural length. This is a conducting movable piston. This is insulated movable piston. And heat cannot flow through this piston, but heat can easily pass through this piston. And let's say we have the heater here. So, let's call this thing piston 1 and piston 2. If the heater is switched on for some time, let's say this area of cross section is A. Volume in compartment 3 becomes half. Find the final temperatures and the heat supplied. Just write the equations. We can't solve, meaning there are just too many variables and all. Let's take it as some helium gas. I just made up this question. Normally the question when only this much used to be the 2 compartments. I just added one more piston. So let's see that. I hope the data is not missing. So one more thing, let's do like this. Let this length be L. This is better. Let this length be L and let this length be L. Area is A. So volume is A into L, which you can calculate. So pressure is P naught, T naught, P naught, T naught, P naught, T naught. So let's get it. First step, draw the final diagram. See how many variables are there. Get me so many equations. That's it. No need to simplify. Just get me the number of variables is got a number of equations. We can always give proper values and make you get the answers, but process is more important for us right now. So there I gave 2 pistons. One is conducting, one is adiabatic. Initially all gas are identical. The switch heater is switched on. And it's observed the third compartment volume becomes half. Let's see, we have enough data. Let's see how will you proceed. Try, you got 2-3 minutes. Did you guys get the final diagram? Let me show you the final diagram. I'm getting a feeling data is not sufficient. Okay. So we have no idea how much actually these things are moved. But one thing is sure. You said this volume became half, so this guy is L by 2. Let this become L plus X. And then automatically 2 length should be conserved. How much is this guy? 3L by 2 minus X. Fair enough. You said the volume became half, right? So the length should become half. Let the right compartment move by X. That means the central compartment should have become 3L by 2 minus x because the total length is 3L. Volume is conserved. That means how much is the spring compressed? What is the compression in the spring? Initially, spring was a natural length was L. Compression in spring, the final length is 3L by 2 minus x. Initial length of the spring was L. L by 2 minus x. That is the compression in the spring. Yes. Let's call it Y. Y is the compression in the spring. Now, the final values here. This guy ka pressure, let's call it P1. If this is P1, this also should be P1. Agreed? Do you agree with that? Y both should be P1? Because the system is in equilibrium, na gods. This force and this force should be equal. Take the two pistons as one system. Then the internal force, whatever is the force between them becomes internal, isn't it? If you take this piston and this together as one system, if this is P1 into area, this is P3 into area, P1 should be equal to P3. It's an equilibrium. Agreed? Because everything else inside is internal. The spring force will cancel. This spring force will cancel. Whatever is the pressure of this gas, P2 into area, P2 into area will cancel. Clear? So if this is P1, this must be P1. If this is T1, this must be T1. Why? Because this is a conducting piston, temperature will be same on both the sides. That's what I'm saying. Putting the data properly is the most important thing. Equations will come later. Let this pressure be P2 and let this thing be T2. Check. Any doubts here? So totally how many variables are there? P1, T1, P2, T2, X. We have 5 variables. You need to give me 5 equations. Get them. Y is also in terms of X. So if you say Y is also variable, there I give you one equation. So Y is something which you already know. So let it be. So 5 variables are there. P1, P2, T1, T2, and X. There are 5 variables. You have to give me 5 equations. Heat is a 6th variable. So that's a different thing. Heat we will see later on. First, you need to find P1, P2, T1, T2, and X. Is this thing clear, everyone? Anyone confused with how I got the pressure P1, T1? Anything you're not convinced here, please ask. Rehan, do adjust your camera a bit. Clear, na? Lakshika, clear? Aditya, Adrit, Ali? Try. I'll give you 2 minutes from here. These kind of questions will be proper advanced paragraphs. Just give me the equation. We'll not solve. The numbers will be added. Previous page is this. Nikha done. Should I show the equations, everyone? Chal, I'll give you one more minute. Get the equations. We have to get 5 equations. अभी कहाँ से आएगा? Figure it out. That's an evil cat. Let's get this. Yasham is the evil cat. First thing, let's look at the left compartment. See one thing. The number of moles in each compartment is same. Agreed? So you can always write the mole equations. That will give you 3 equations from there directly. For the first compartment, P naught, V naught. This is P naught A into L by T naught is equal to P1 A into L plus X into T1. For the second compartment, P naught A into L by T naught is P2 into A into 3L by 2 minus X by T1. The third compartment, P naught AL by T naught is P1 A into L by 2 by T2. These are 3 equations. And in third compartment, we have one more thing. The third compartment is also an adiabatic process. So we also get P naught V naught power gamma is equal to P1 V naught by 2 whole power gamma. From here, actually, you get P1. Game starts from here. This is actually question you have to solve now. You start from here. So P1 आ जाएगा. Put P1 here. T2 आ जाएगा. You start getting everything from here. You still need one more equation though. This is equation 4. Where is the fifth equation?
TV to the power 1 minus gamma constant.
P, which one you're talking? Which gas?
E power gamma minus 1.
For the adiabatic, third compartment.
Yes.
Yeah.
Array gods, once you use this already, adiabatic ka use kar liya. You're not using any new equation. If you use TV per gamma minus 1 or if you use PV per gamma 1, isn't it the same adiabatic thing? You're not creating a new equation, isn't it? Logical ऐसा सोचो ना, PV पर gamma से ही आपको TV पर gamma minus 1 आया, right? By substituting PV is equal to nRT there, you got this thing. So for the same gas, if you apply 2 different forms of the same equation, you won't get an unique equation.
So can
You're
we
still
use
forgetting.
conservation of energy?
Okay, what is the initial energy? Heater तो switched on ना, Anika. Energy कहाँ से conserve हुआ? Heat is coming from externally.
So कुछ spring से related.
Spring से related. That is a word. Did you observe one thing? कहीं पे spring use नहीं किया अभी तक. Take any one piston. You can take piston 1 or 2. It doesn't matter. I think you'll get the same equation. This side will be P1 into area. This side will be P2 into area, and the spring force will be Ky. So from here you get P1 into area is P2 into area, K into Y. Y is L by 2 minus X. That's your equation 5. If you take the right compartment, क्या होगा? Right compartment also will be same actually, ना? Left piston or right piston will give the same equation 5. There, 5 equations, 5 variables. Please check the equations. So one thing is clear, always the number of moles you can use. Check for adiabatic processes and the piston ka force equation. What about the heat supplied? What will be that? Think I'll give you another minute for that. Anyone confused with what I did here, please ask me. Don't hesitate, get it cleared. Anika, you're getting now why energy can be conserved? You're supplying energy from outside to a heater. So, and that is the next question. Find the heat supplied by the heater. Clear? Let's see. Right, Anusha. Now, Vidyut, previous page you want? It's just a question. Clear? Now see, whatever heat you supplied, this is the energy flow diagram. The heater gave to the compartment 1. The compartment 1, it is used to increase this thing, internal energy. Then this went to piston 1. Piston 1 increased the internal energy of this thing. And the spring energy half k y square. And the remaining went to piston 2. Piston 2 increased the internal energy delta U3. So end of the day, what you have to see is finally where did you end up? So the heat supplied will be the change in internal energy of the 3 compartments. Now extra spring is sitting here, so half k y square. Check. You're right, Anusha. Adrit, what is that work exactly? Which work are you talking about? When you say work, do, what is that exactly? You need to understand whatever work you did on this piston, since it's an adiabatic process, that only is becoming internal energy, na?
But the first compartment is also doing work on the second compartment. And some of it is going in increasing the energy of second, and the second is also doing work again.
So what is that work doing finally then?
And it is going into third compartment internal energy.
Okay. So what happened to the work?
Some of it will go in potential energy.
Eh,
of
eh,
spring.
eh, eh. Okay, so that is this only, na? So you should not add any work in the middle. That's what I was saying. Whatever work you done on the piston 1, that itself becomes internal energy and spring energy. So it's not like spring alag hai, work alag hai. You're getting a point?
But that is doing work on the middle one, and the middle one is again doing work.
Arey God, Adrit. When you say work, you're saying, do you conserve energies? Do you conserve works? Is work energy? Let me ask you this question.
Yes, it's the same.
Is work energy?
It is mechanical energy.
So you mean to say work and energy both are same? I should punch you. This is what happens when you don't revise the notes.
The capacity to doing work is energy.
You and your capacity to do work. Energy is a quantity. What is work? Work is an act of transferring energy. It's like when I give you 100 rupees, right? That is work. If you have 200 rupees, that is not work. That is the amount of money you have. It's like, tell me one thing. You have 200 rupees. If I give you 50 rupees. So do you have 200 rupees or 50 rupees plus money that I gave 300 rupees? You get the point? Whatever I gave, that only is coming as storing, na? Work is not energy. Are you getting it? Work is the process of transferring energy. So it is like this. The piston did some work on piston 2, that became internal energy of the gas 3. That is a process. That is like a verb. You're getting the action of transferring energy is called work. Are you getting this? Work and energy are not same. Be careful. Is that point clear, everyone? You just need to see like this. I gave you 100 rupees to the compartment 1. What did the compartment do? The compartment stored, let's say, 20 rupees. Remaining 80 rupees, it went in the form of work to piston 1. You're getting work only. It is giving 80 rupees to the piston 1. That process of giving 80 rupees is called work. I hope you're getting the point. When I say I'm giving 80 to piston, that is called work. Now, what did the piston do? It gave, let's say, 15 rupees to this guy, and let's say 15 to this guy. Then remaining 50, piston 1 did work on piston 2 through the spring, and this 50 went through this and got stored here. So eventually your 100 becomes 20, 15, 15, and 50. I hope you're getting the meaning of this. So the process of transferring energy is called work. Work is not stored. What is stored is energy. Is this thing making sense, everyone? Clear? Clear, na? Be careful, because even I used to get confused on that. So the best thing to do is forget about work and all. Just finally see where is the initial energy, where is the final energy. Bas, beach mein whatever happened, the work did all that. Clear, na, Aisha? Got this? There. So these are some of the questions, on thermodynamics first law, especially the efficiencies, the springs, and all this stuff. The next thing, second law of thermodynamics. Now in JEE mains portion, they did remove these heat engines and all, like I said last time. But we will just finish off little basics. Because advanced mein abhi tak they didn't say anything, so better we know. So second law of thermodynamics. So first thing, second law, right? There are multiple forms of second law. One for chemistry purpose, there is one. Physics may be most interested in heat engines. So our second law will be mostly for heat engines. I can add that. So what it says is, first thing is Clausius statement. It is impossible for a machine to transfer heat from a cold reservoir to a hot reservoir. Basically from a cold body to a hot body. Without external work. Another statement is a heat engine working between two temperatures in a reversible process. Now in physics, all processes are reversible process only. But what happens, right? In reality, reversible processes don't exist. So what we say is quasi-static. Quasi-static meaning, static means what? The system is in equilibrium. Quasi matlab, we will say momentarily it is in equilibrium. We really need not worry about that word. Quasi-static meaning simply it's a reversible process. See, I'll tell you a simple reason for that. For example, let's say there is a container here with, let's say, some temperature T naught. If you give suddenly heat Q, what happens? The place where you gave the heat, suddenly temperature will go to 4T. Here temperature will be 2T. Here will be temperature T. Here will be temperature T. Here it will be T. Here it is 3T. Isn't it? After some time, the whole compartment ka temperature becomes 2T. So during this stage, is the temperature defined? Temperature is not defined. Getting it? So that means we can't use ideal gas equations. So what we assume is, instead of saying we are giving so much heat, you are giving such a small heat dq, dq, dq. We are assuming the whole compartment is increasing by T plus dt, T plus 2 dt, T plus 3 dt. So we are assuming at every instant the system is in equilibrium. Such a process is called quasi-static or reversible process. Clear? That's it. There are no questions, nothing on that. That much idea you should have. Chemistry method you must have done reversible, irreversible, and detailed. I hope they did. So we are not getting into that because physics may it really doesn't matter. We do everything is reversible only. Because the moment you say irreversible, meaning intermediate stage mein pressure and temperature are undefined. If they're undefined, our equations are wrong, our graphs are wrong. You can't do anything. So an heat engine working between two temperatures in a reversible process cannot be more efficient than a Carnot engine working at same two temperatures. So we'll see what is this Carnot cycle. There is another statement here, Kevin Planck statement. There is all different forms of second law for in physics. In chemistry, the second law will be like what? The reaction always proceeds in the direction of increasing entropy, isn't it? They do talk in terms of Gibbs free energy, entropy, and stuff. A heat engine cannot convert all heat into work. Basically, it's saying you cannot have 100% efficiency. No. What's a cycle? Carnot, he figured out there's a particular cyclic process in which you get maximum efficiency. I will not get into why and all that. We don't need it. But let's see how the process looks. So in this AB, is a reversible adiabatic expansion, isothermal expansion. So first the gas undergoes an isothermal expansion, then it undergoes adiabatic expansion. Then it undergoes isothermal compression. Then again you have reversible isoadiabatic compression. So in this process, right, A to B, when you go, the temperature is constant and you absorb some heat Q1. B to C, heat is 0 because it is adiabatic process. C to D, temperature T2, you reject some heat Q2. And again here delta Q is 0. So if I try to put this cycle in a diagram, for heat engines, this is what we do. We have something called source. Source is high temperature. The heat is taken from the source, maybe your steam engine or something where you're putting coal and burning. You're supplying it to the engine. The engine, what it does, it burns, it gives you some work, but also some heat is rejected to the atmosphere and all. We call it sink. Basically, sink is anything which is low temperature. So it takes heat Q1 from the source, it rejects Q2 heat, and you get some work W. So the main things to remember in this process, the heat observed Q1 by Q2 will be in the ratio of T source by T sink. Like I said, the proof is not important. We'll not get into it right now. Mains mein to hai hi nahi. Advanced also that proof is not important. So this is one. So from here we can get the efficiency, and we also know Q1 is nothing but the work done plus heat rejected. So from here we can define efficiency is work done by positive heats. This is Q1 minus Q2 by Q1. So this will be 1 minus Q2 by Q1, which is 1 minus T source by T sink by T source. There, this is the formula which you need to mug up. So for any heat engine, you can't have an efficiency more than this. Tomorrow, if some guy comes with a design and says, my engine gives you 40% efficiency, and you ask him what is the working temperature, then he says, the engine temperature goes to, let's say, 500 degrees, and outside temperature is 30 degrees. So if you substitute these values in Kelvin in this, and let's say you got 35, and he says for efficiency is 40%, he's bluffing you. You're getting it? Meaning, suppose if, let's say, he gets 50%, he might be right, he might not be right. But you can't have an efficiency more than Carnot cycle. You can put on that formula. Let's see a few questions on this. Questions were quite easy on this, actually, mains mein. I don't know why they removed this. Let's see. Previous page here. Let's see a question. This is 2013 ka question, I guess. 2011. Get this? First thing, the problem here, you know what? He didn't mention who is T1 and who is T2. We don't know who is sink and who is source, isn't it? So first you need to figure out that. Why are you assuming one is sink and one is source without understanding? Now see, look at the formula efficiency. 1 minus T sink by T source is the formula. Now try to understand. He's saying when T1, T2 are there, efficiency is 1 by 6. Fair enough. When T2 is lowered by 62, efficiency increased. So logically, socho. If T2 was sink, suppose if T2 was sink, that is a numerator. If I decrease this number, will the efficiency increase or decrease? Efficiency would increase, right? Because it is 1 minus na. Suppose if T2 was source, if you decrease this number, the whole thing would have increased and the efficiency would have decreased. Is that making sense? So therefore, T2 is the sink. Is that making sense? Since efficiency increased, so that is the first thing you need to figure out who is the sink and who is the source. Since efficiency increased when T2 decreased, T2 must be sink. So initially efficiency is 1 by 6 is 1 minus T2 by T1. Now you're saying it became 1 by 3 when T2 decreased by 62. Make sense? Okay, na big question. So from here, if you solve, you'll get T1 is equal to 372 Kelvin. Yeah, that's right. Easy question, but you should know what you're doing. Clear? Let's see one more. Yeah. If you have taken T1 as sink, the whole thing would have been for a toss. Let's get this thing. Let's see. 250 Kelvin. The efficiency of the heat engine whose sink is at a temperature of 300 Kelvin is 40%. So 0.4 is 1 minus T sink is 300. T source discussion is not there. So we can calculate from here anyways. So that's 0.6. So T source is 500. Now he's asking to increase the efficiency to 60%. Keeping the sink constant, the source temperature should be increased by. This is 750 Kelvin. Therefore, change in temperature is 250. Easy. That's a little different one. Just a formal application there. Any doubts on this? Next one. Carnot engines in series. Let's say we have a source. This is your engine 1. Okay. And that is given to a sink. So in this process, you get some work. So you are giving heat some Q1. This rejects heat Q2. And you get some work F1. Eta 1 is the efficiency of the first engine. Then what you did smartly, whatever heat that you reject here, instead of wasting it, you connected a second engine in series. Normally in power plants, this is what they do. After that first engine is run through, whatever steam is going away, they collect that steam and they reheat the steam. And again, they run the turbine through that. So this way, they extract another 4 to 5% more. And finally, they let it out. So in this process, whatever you rejected here, Q2, that entire thing you send to engine 2. So that will reject some Q3 and you get a work down W2. And eta 2 is the efficiency of second engine. Right. So find the efficiency of the full system. Answer will come in terms of eta 1, eta 2. Find efficiency of the full system or full process. So only engine 1 would give you efficiency eta 1, only engine 2 would give you eta 2. If I have both of them in series, then what is the efficiency? Then we'll get a very good answer. What if there are 3 engines in series, 4 engines in series? We'll get a sequence. First, let's get this. You'll see a good answer. It's a very interesting sequence. Answer comes in terms of eta 1, eta 2, God. That Q1, Q2, all I just gave for you to understand. Aryan, clear na? Eta 1 and eta 2 are known. Remaining all, I don't know. All those Q1, Q2s, we don't know. Try. I'll give you a minute. Her with youth. Solved it so fast. Others, try. You got a minute. Clear? Hanika, you got it right. Adrit, that looks weird. Aryan, Anusha, you got it. Second one is right. Let's see. So the main idea here is efficiency eta 1 is what? W1 by Q1. Okay? And W1 is Q1 minus Q2. Efficiency eta 2 is W2 by Q2. And W2 is Q3 minus Q2. Fine. Now what you want is efficiency of the full cycle. That is the total work done, W1 by W2, and the heat given is Q1. So this is W1 by Q1 plus W2 is eta 2 Q2 by Q1. W1 by Q1 is eta 1. And Q2 is what? This guy is not important. Q2 is Q1 minus W1. This will be eta 1, eta 2 minus eta 2. W1 by Q1 means eta 1. There, that's your efficiency. Eta 1, eta 2 plus minus eta 1, eta 2. So you know how you get the answers? Just try to arrange the terms there. Check it out. So if you have two engines in series, I'll turn the page, have a look at this. Did you guys study Venn diagrams in school? So if this is eta 1 and eta 2, so what is this area here? Eta 1 plus eta 2 minus eta 1, eta 2, intersection area. It kind of looks like that. If you do for three engines, can you guess how will the answer looks like? This intersection, right, is eta 1 union eta 2. We'll write as eta 1, eta 2. If you have three engines in series. Now, can you guess what will be the answer? Eta 1 plus eta 2 plus eta 3 minus intersection of eta 1, eta 2 minus intersection of eta 2, eta 3, intersection of eta 1, eta 3 plus intersection of eta 1, eta 2, eta 3. You guys know that Venn diagram thing, the areas and stuff. So the answer comes as if there are Venn diagrams. Clear? That's the sequence comes out like this. When if you do for three engines, you'll find the answer comes out like this. So have a look at this. There are a few more varieties, but I think we'll not do it. We will see later on. Mains mein to nahi hai, but when it's there for advanced, we will see it then. But this much is sufficient even for a bits level. Bitsmith is still there. They don't ask anything. This thing is also a little higher. Clear? Take a break. Come back by 7:05. We'll continue from here. Still have one entropy and refrigeration ka cycle. I'll just teach you that. We'll be done. We'll start off with conduction today. Take a break. Any doubt so far? Anything you're confused? Please ask me. Or else take a break and come back by 7:05. Page 3. 3 engine page. Okay, this guy. Any other doubts in today's class? Okay, come back in 5-10 minutes. I'll be back sometime. Chalo, cams on everyone. The next thing is the refrigeration cycle. The refrigerator is reverse. So in this, what we do, we have source, we have that engine, we have the sink. We take heat from the sink. To do this, you need to provide work. Basically, that's your electricity. And you throw Q1 outside. So when you use a refrigerator, right, or AC, think of like this. So let's say you have an air conditioning AC. So sink is your room. You're trying to make it cold. And you're throwing the heat outside to the atmosphere. So your refrigerator inside is your sink and outside is the what you call the source, the higher temperature one. So for this to happen, you need to provide electricity. The same formula is applicable here. Q1 by Q2 is T source by T sink. But tell me one thing. Here efficiency ka meaning nahi hai. In AC or refrigerator, what are you actually interested in? How much heat are you removing per unit work, isn't it? Let's say if I supply 1 joule of electricity, do you want to remove more heat from the room or less heat from the room? You want to remove more heat from the room, isn't it? So this is what actually happens. So we provide electricity to AC. It removes heat from a room which is cold and throws it to atmosphere. So what you're interested here is, we call it coefficient of performance. Beta, which is the amount of heat taken Q2 by W. So W is Q1 minus Q2. Bring that Q2 down. This will be 1 by T source by T sink minus 1. So beta is given by Q2 by W is T sink by T source minus T sink. In case even if you forgot the formula, right, remember what you're interested in. You wanted interested in Q2 by W. This is the formula. Now from here, we can also get something interesting. If you look at the work done, we get Q2 into T source minus T sink by T sink. What is the meaning of that? Think of like this. As you're removing more and more heat, T sink will tend to 0. So if the T sink is tending to 0, the work done will tend to infinity. So it becomes more and more difficult to cool down a system. So this is another proof that you cannot reach a 0 Kelvin, because to reach 0 Kelvin, you need infinite work. Means cooling down a system. Let's say if you're using your AC from 24 to 20 degrees and 20 to 16 degrees, that 4 degrees ka difference, right? You actually consume more than at least 20-30% more electricity. So as T sink tends to 0, work will tend to infinity. Therefore, 0 Kelvin is not possible. You cannot achieve 0 Kelvin theoretically, practically. Have a look at this. Others, do keep your cams on. Right? Next thing. Let's see a question on this. Let's get this. There, you can copy it on this formula if you want. Beta is T sink by T source minus T sink. Clear? Get this. A refrigerator's quotient of performance beta is 5. Extracts heat from the cooling compartment at 250. How much work per cycle is required to operate the refrigerator? How much heat per cycle is discharged to the room which acts as high temperature? Meaning, he's saying this is Q2. This thing is Q1. Right, Swastika. Get it, easy one. Clear? Yeah. So first thing, I just apply the formula there. So beta is Q2 by W. You're saying this is 5. So this is 250 by W is equal to 5. So W is equal to 50 joules. Q1 is nothing but Q2 plus W, 300 joules. Easy. So let's say I give you two options, okay? Let's say it's very hot and you have two options. Option 1, you can take an ice block and sit in the room. Option 2, you can have a refrigerator in the room. You can open the refrigerator door and you can sit. Which is a good option? Which will be a comfortable option? Again, listen to the question. It's very hot and there are two options with you. It's a completely insulated room, closed. Option 1, you can have an ice block, take the ice block with you in the room, sit there. Case 2, you can have a refrigerator connected to a power supply. You can just open the door and sit there. Which one is a good option? Think about what happens. See, if you have a refrigerator and if you open the door, fine, you'll feel cold, great. But what you're doing is whatever heat that you're taking from here is thrown from the backside of the refrigerator. It's not an air conditioning refrigerator. Refrigerator outdoor unit is where? It is inside only, right? That means whatever heat, electricity that you're supplying, that becomes extra heat, isn't it? Example, in this question, you removed 250 joules of heat from the compartment. You throwed it out plus added electricity. So in the second case, eventually the room will become more hot. Is it making sense? But if you want to feel cold, best thing will be to go and sit inside the refrigerator and close the door. That would be a better option. Then you will feel cold, but you will suffocate and die because there's no oxygen. So clear? So that's a bad idea. Your refrigerator actually acts like a heater because it is pushing out all the heat from inside and throwing it out, and the electricity is becoming heat. Clear? Next one. Entropy. The symbol is S. It's a parameter which gives disorder in the system. The formula is ds is dq by t. So we can write delta S is dq by t, or delta Q is integral TdS, which is area under TS graph. Have a look at this. Clear? Let's see a question. In a certain process, the heat is given by K into T. K is constant, T is temperature. Find the change in entropy when temperature changes from 100 to 200 degrees. Get this easy one. Too much is the formula for entropy. Delta S is integral dq by T. Yep, you guys got it. So that is one thing you have to be careful here. Temperature should be in Kelvin. So delta S is dq by T. Q is equal to KT. So dq is equal to kdt. This is kdt by dt. Be careful, the limits are 373 to 473. There. Easy? Yep. Palaksh, clear with this? Nolika? Ali? Aryan? Neil? Next one, turning the page. Next one. Entropy is there in the portion, huh? T versus S graph. This is S naught. This is 2S naught. This is T naught. This is 2T naught. A, B, and C. Find the efficiency of the cycle. So they'll give you in terms of T and S, and they can ask efficiency of the cycle. Let's get this. Right, Adrit. Anyone else? We have one answer so far. नहीं आ रहे नंबर आएगा रे डायमेंशंस मैच नहीं हो रहा तेरा let's see now in this TDS graph, right, the area under the graph gives you the heat. So when you go from A to B, so this area will be half into sum of the opposite sides, 3T naught into S naught. And you're getting positive. So QAB is 3 by 2 S naught T naught. QBC is 0 because DS is 0. There's no area. Whereas QCA will be minus because it's decreasing T delta S, so T naught S naught. So remember, this is the heat rejected, that is the heat absorbed. So what is work? Work will be positive heat minus negative heat. That is 3 S naught T naught by 2 minus T naught S naught, which is S naught T naught by 2. So what is efficiency? Efficiency is work by only positive heats. Check. Easy. So in this cycle ABC, A to B you're giving positive heat means system is absorbing heat. C to A it is rejecting heat. B to C it is doing nothing. So heat absorbed minus heat rejected. What happened to the remaining heat? That should be the work done. the work done by total heat given is the efficiency. Clear? Next thing. All got this? Clear? Haraksh? Clear, na, Anika? Great. With that, we're done with thermodynamics. Next thing, heat transfer. Heat transfer has three parts: conduction, radiation, and convection. Now again, in convection, right, they removed it from the mains portion. But we will do one or two problems because it is there for boards also. So let's see conduction part. So till now, right, we kept on saying heat is given, temperature change and all that, but great, but how do you actually give heat to a system? So heat can be transferred in three different ways. Conduction, convection, and radiation. So in our portion, primarily we study conduction and radiation. So first, let's do with the conduction part. So heat is transferred from one point to another due to molecular collision. So the actual transfer of matter. So basically, it is due to the molecular collisions. Now, what happens here is, we know the molecules that's inside a lattice are vibrating continuously. We have seen this in thermal expansion also. Right? And we know the kinetic energy of these molecules is how much? 3/2 kT. So this is proportional to amplitude. So bigger the temperature, the more they vibrate. Or you can say this is also proportional to velocity half mv square. So higher the temperature, faster they move. And we know from collisions, if you have two bodies of same mass, u1, u2, E is equal to 1. This is before collision. After collision, the exchange velocities. This guy becomes u2 and this guy becomes u1. So something similar happens here also. So when the exchange velocity is meaning the colder one becomes hotter, the hotter one becomes colder. Clear? Now, what happens exactly? Let's say you take a metal rod and you keep a heater here and you're putting a flame. So what happens here? Heat flows from one side to another side. So when you say heat is flowing, exactly what's happening? The molecules on the left-hand side will gain more energy because they're getting the heat from the heater directly. They collide with the right, transferring energy. And this just keeps on transferring. You must have seen this, right? If you take a spoon, put it on a stove and you catch it, after some time your hand burns. Even though you're not in contact with the flame directly. So this is how it looks. So as you're giving more heat here, these molecules have higher amplitudes, these molecules have smaller amplitudes. So when they collide, they exchange velocities. These are less amplitude or less slowly moving. These are higher amplitudes. So after collision, they'll exchange velocities. So the left side actually cools down, but because you kept a heater, temperature will again increase and so on. So while studying this, right, what we do, we study something called a steady state. Not only this chapter, we'll again encounter something similar things in fluid mechanics, current electricity. We study something called a steady state. What's a steady state? The property at a point does not change with time. But different points can have different velocities. Property can change with position but cannot change with time. Example, let's say we have a road. You must have seen the speed limits. So let's say any car that enters here, 20 kilometers per hour is the speed limit, meaning let it be a car, vehicle, anything that comes here should have a speed of 20. But when the same car goes here, let's say the speed limit here is 40. That means if you observe, the speed of the cars at a given point is constant. Is that making sense? Speed of the car is not constant. Any car that reaches here will have a speed of 40. But the same car, when it goes from here to here, maybe the speed limit is 10 kilometers per hour. You're getting it? So basically, at this point, think about it. On the road, let's say if the speed limit is 20 kilometers per hour and everyone is strictly following. So most of the cars will have a speed of 20, right? At that point, the moment you go ahead and let's say speed limit becomes 60, then most of the cars will have a speed close to 60. So is the speed of the car constant? No, but speed of the any vehicle at a point is constant. Is that making sense? Right? So at this point, let's say speed limit is 10 kilometers per hour. So what this means is speed of any vehicle at this point is constant, whereas speed of the vehicle is not constant. We say the traffic is in steady state, meaning all the cars, right, at a given point have same speed. Once you go ahead, the speed will keep changing at different points, but the speed at a given point is same. Whereas speed of the car can change. We say the traffic is in steady state. The traffic is going steadily. Have a look at this page. So let's see how this works in temperatures. Let's see. Previous page here. Let's see how conduction looks.
Showing you the world's fastest heat conducting material. And then I'm going to cut it open and show you what's inside of it and how it actually conducts heat so fast. So first, I'll show you how fast this thing actually conducts heat. It's pretty amazing. It's almost instantaneous. I have two rods here. One of these is just a regular copper rod. Now, copper has a very high thermal conductivity. It's one of the fastest conducting metals in electricity. Okay, so now we're going to try to actually see.
So what
this
they're going
heat
to do,
transfer.
right?
So I'll put my copper pipe right here. And then I'll put my heat pipe on the other side here.
So there is something called a heat pipe, and there's a regular copper rod. So regular copper rod is a solid copper rod like your pen, completely solid. There is something called a heat pipe. We will talk about that later on. So, but that is one of the fastest conducting thing. See what happens. So this paper, right, it reacts to temperature.
So when this stuff gets cold, it turns black.
So whenever it is cold, right, it becomes black. So when the temperature is normal, it becomes
So we
bluish
should
again.
be able to easily see the heat transfer from the pipe to the ice when I stick ice on both the copper pipe and the heat pipe. Okay, so what I'm going to do is I'm going to set ice on the heat pipe and the copper pipe, and we're going to see how fast the heat gets transferred from the pipe to the ice. Okay, 3, 2, 1. Whoa, it just instantly turned it black here. Pipe.
See that again. So this paper, right, that is what tells you whether the heat transfer is happening or not. So if the pipe gets cold, the paper becomes black.
To the
So
ice.
he's going to keep an ice.
Okay,
The upper one is a
3,
heat pump.
2, 1.
Heat pipe. You can see how that becomes entirely
it
black.
Just instantly turned it black here.
Here you can see the copper pipe,
Now
that is the conduction.
Slowly moving up the copper pipe. That is awesome.
So here what is happening, I'll tell you. On the left hand side, there is an ice. So it is getting cold. Means molecules are vibrating slower, isn't it? So they are stealing energy from the right hand side to the left hand side. So the molecules on the right hand side are becoming slower. So that's what we mean by cold. You can see the conduction moving actually. The heat is getting pulled out.
You can see how long it takes to move up the copper pipe. Okay, we've heated both of them up now. Let's set our ice
Now
on.
reverse. Now they heated both the rods and they kept the paper. Now when you heat it, it looks bright.
Okay,
The upper one is a
3,
heat pipes.
2, 1.
Now we kept an ice. Look at the upper one, it's pretty fast.
Look how fast this one turned black. The heat pipe was almost instant.
Same thing. Now the rod is hotter, the heat is being pulled out.
And then the copper pipe, you can see the heat slowly coming out of it. What's really neat with this is by just using the heat in your hand, you can actually cut through ice like it's a razor blade.
Heat pipe is a pretty interesting concept.
It cuts through the ice. Why this can transfer heat so much faster than a regular copper rod. This can actually transfer heat around 2 orders of magnitude faster than a copper rod. Kelvin. Hold this.
If you actually break the heat pipe, you will see what is that he's breaking and showing us.
See in here.
It is actually a hollow thing.
So you can see the inside of it. It's not just like a smooth copper pipe inside of it, but it's actually really spongy. So the sides of the wall here are almost like it's a sponge. And the reason that that's in there, because inside of this, there is actually a little bit of water. And usually what they'll do is they'll get a regular copper pipe and they'll fill it with a little bit of water, and then they'll let that water boil, and then they'll seal off both ends of the pipe. So that all that's left in there once it's sealed off and cools down is a tiny little bit of pure water in a vacuum. And so there's a really low pressure in there because the water that was hot vapor condenses down once it cools down, but the ends are sealed, and so basically.
So they're actually using convection in that. Let me tell you how it works. So normally in industries and all, right, we use heat pipes for fast heat transfer. So what happens in that? You have a pipe there. So this is sealed and this is sealed. It's a vacuum inside. You have a small water drop here. And everything is almost vacuum. Little water is there. The moment you heat this water will vaporize. The moment water vaporizes, this is a high pressure region and this is a vacuum here. So what will happen? The water will rush now. You're getting it? So suddenly it becomes hot here. That is the reason you can see the transfer looks almost instantaneous. Whereas in case of a pure solid conductor, what should happen? There are collisions. It is taking time for the heat flow transfer. So inside the heat pipe, basically what you're doing is convection. Clear? So that's called a heat pipe. I'll post the video in the group. You can check it out. That paper, I don't know what is that called. It's some paper which reacts to temperature. So, but I hope you saw how the conduction looks, right? So that is how you can visualize conduction. The energy is being pulled out. Clear? Now, what does a non-steady state look like? So non-steady state. So let's say we have a rod at 0 degrees. We have a heater here, and let's say you're giving some heat. Let's give some number. Let's say you're giving at a rate of 100 joules per second. Let's say you're giving 100 joules per second. So initially what happens? Suddenly everything will not go. So this temperature will rise to 100. This temperature will be some 80. This guy will still be 0. This guy will still be 0. This guy will still be 0. So you're sending 100 joules per second. Maybe here there's only 80 joules per second. Heat is getting absorbed. Maybe here there's only 30 joules per second. Right? And maybe eventually only 10 joules per second is coming in. So if you see here, heat is absorbed by the rod to increase temperature. So whatever is going in is not coming out. This is not steady state. Steady state meaning the flow is constant. Heat is absorbed by rod, to raise temperatures. So what happens? Suddenly everything will not go. 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 Sud So inflow is not equal to outflow. So this is a non-steady state. So that's how simply you can say. It's like if 10 cars are going into the road and if only 4 cars are coming out, it's not a steady state. Then eventually, after leaving it for a long time, this will become 100, 90, 80, let's say 30, 20, or let's say 20, 10, and let's say this is 0. You're sending 100 joules per second. 100 joules per second is flowing and 100 joules per comes out, meaning you reached a steady state. Inflow is equal to outflow. Now see, at different points, temperature has changed, but the temperature becomes constant now. At any point, the temperature will not change with time. This steady state, that's a simple way to remember what is steady state. Inflow is equal to outflow. Whatever heat you're sending, all the heat should come out. And we will be studying only steady state cases. Clear? Get the meaning of steady and non-steady state? Think like this thing, no? Let's say we have an empty road, right? And you released a gate or something, and let's say 100 vehicles went into the road. Do you think at the same time 100 vehicles will come out? It takes some time, right? Let's say the road is like this, bottleneck. So 100 vehicles have gone inside, but only, initially only 40 vehicles will pass through. Some of the vehicles will start getting stuck here. And because the vehicles are getting stuck and these people are honking, what will happen? So instead of 100, only 80 will enter now, but here 60 will go. Still, it is a non-steady state. Now, there's a pressure building up because of the traffic. So only 60 vehicles will enter, or maybe 50 vehicles will enter, and only 50 vehicles will leave. Eventually reach a steady state. Doesn't that happen near toll nakas? Ever observed? You're going on a vehicle, you're going full speed, suddenly the vehicle the entire traffic just comes to standstill. So your net speed will become the speed of at what rate the vehicles can pass the toll naka. In chemistry, we call it rate determining step. The reaction can proceed as fast as the slowest step in the reaction, which is SN1, na? Kind of like that. Clear? So, how does heat flow in a steady state look like? We'll just finish off the theory today a bit. So we'll be studying primarily steady state cases. Consider a cylinder of length L and cross-section area A. The ends are maintained at T1 and T2. Let's say this is T1, this is T2. Let's say T1 is greater than T2 and the heat flows from here. Okay. So what this, again, completely experimental, dq by dt, that's your heat flow, is given by minus Ka by L T2 minus T1. So here, dq by dt is your heat flow per second. This is also called as heat current. This thing, right, kind of looks like, we will see, it looks like resistance is Ohm's law. K is called thermal conductivity. We'll talk about this a bit later. but the physical significance is higher the K, more easily heat transfers. So it is like conductance. Resistance is like what? Opposition. K is like conductance. Higher the K, more easily heat conducts. Example, K of metal is greater than wood. Did you ever notice this thing in winters? When you go and sit on a table, you know the wood and the metal both are at same temperature, but the metal will feel more cold. So what are you experiencing actually? Are you really experiencing temperature? What you're experiencing is heat flow. If you're experiencing temperature, wood and metal at the same temperature, both should look same. But when you touch the metal, because the conductivity is more, you lose more heat per second compared to wood. That's why you feel metal is more cold even though the temperature is same. A is the area perpendicular to the heat flow. L is length along the heat flow. And negative indicates heat flows from high temperature to low temperature. If we talk about this K here, K for a perfect conductor is infinity. K for insulator is 0. Just keep this in mind. And this is cross-sectional area perpendicular to heat flow. So this is the basic thing. So we will wrap up with this. So next class when we meet, we'll continue from here. There is a differential form of this also. We will put it down and then we'll start with the problems. So conduction is pretty cool. It just looks like resistances and stuff. So mostly next class, we will wrap up conduction and then mostly next Friday, we should wrap up radiation. Let's see how it goes. Basically, since the convection is not there, should it take a little less time? But mostly next Friday, we will try to wrap up the chapter though. Okay, so with this, we'll wrap up for the day. So the paper is online till night today, 11 o'clock. So make sure to give. Right. So any doubts, anything you can stay back and ask, also free to leave. So take care, stay safe. I'll see you guys again next Wednesday at the same time.